Honors Chemistry, and this is going to be a quick run through of the Endo demo, which would take a little bit longer in class, and I would actually have a rack of test tubes set up for you to look at things. In this case, the only demo that you may be able to actually do is going to be demo number 4, unless you actually have a one of those athletic cold packs at home. And the demo number 1 is actually one of those athletic cold packs. So that kind of gives it away here. In demo number 1, we're going to take some ammonium nitrate. And in the cold pack, if you do have one of those cold packs, go ahead and go get it now. The ammonium nitrate is the solid, the crystals that you feel inside the cold pack. And inside the cold pack, there's a little inner pouch that you're supposed to burst. And that inner pouch in the cold pack actually has water in it. So that water in the inner pack then is going to be released and is going to dissolve the ammonium nitrate. And when that happens, as we said, it gets cold. Now, a cold pack is cold because the reaction absorbs energy from the surroundings. So if we absorb energy, whenever you see that word cold, we're going to think that let's rewrite that. The system absorbs energy from the surroundings. And because the system is taking in energy, that's going to be an endothermic reaction. And so the delta H, let's put a plus sign up front here, is a positive 26 kilojoules per mole of ammonium nitrate. The next reaction, this reaction we actually saw in our eudiometer lab. This was magnesium metal and hydrochloric acid. And if you recall, maybe you recall that the eudiometer, the water did warm up a little bit. So it's not so far out of the question for you to remember that the surroundings got hot. So this hot surroundings means that the system releases, sometimes we say loses, energy to the surroundings. And since the system is losing energy, the energy is going out. That's an exothermic reaction. And because it's exothermic, as we saw in the notes, the potential energy of the system goes down. And so we're going to put a negative sign in front of this and make it negative 464 kilojoules for every mole of magnesium. Demo number 3, this is kind of a fun one to do. And Dr. Don Showalter in our video had a lot of fun with this one. Whoa, look at that. This was when he mixed the two solids. So the barium hydroxide, which was a hydrate, so this was the hydrate, is a solid, and the ammonium thiocyanate was also a solid. We mixed them together and stirred it, and it got really, really, really cold. It actually did get down, and if we had this in class, we would see it gets down to about about negative 20 Celsius, about 0 degrees Fahrenheit, if you want to look at that. And so this does get cold, and it was cold enough. You know what? No, I was going to use blue for cold. That's okay. I'm using red still. So got cold, and if you remember, this did freeze the beaker onto the board because it got so cold that it was able to freeze the water. And so that's an endothermic reaction. So we're going to put a plus in front of the 130 kilojoules per mole of the barium hydroxide. It would also be for every 2 moles of the ammonium thiocyanate. And so that would become a stoichiometric ratio you could use. And as Dr. Showalter mentioned, we smelled ammonia coming off, and you can't, but let's just put a Y, put a yes. Okay, why am I not writing? Put a yes in there. Let's pretend we smelled the ammonium nitrate. Now, the next one, you can do this one, and if you have your relaxed rubber band, don't stretch it yet. What you want to do is you want to hold the rubber band. It's got to be a pretty heavy one. It's got to be a thick one. Don't get a thin one, otherwise you won't be able to feel anything. Okay, let's see if this is going to stay this time around. So you want that heavy rubber band, so a thick one, at least 1/4 of an inch thick if you have one of those. And put it in contact with either your upper lip or your forehead, and it should feel like room temperature. Now remove the rubber band from your skin and quickly stretch it. And as it's stretched, put it on back onto your lip or your forehead. And you should feel something. You should feel a temperature change. You might have to repeat this several times because the temperature change is very slight. Do it a couple of times until you're sure of your temperature change. So what did you feel? So you should have felt that it got warmer. And so this is an exothermic reaction. Now, the reason it's exothermic is, we're going to start looking at this in a few days, is that when you go from a relaxed rubber band to a stretched rubber band, the stretched rubber band, it makes the molecules line up. So all the molecules are now lined up, and so the entropy is going down. And the only way to have a decrease in entropy happening at the same time, that means that the enthalpy the enthalpy of the reaction is also going to go down. It's going to get the enthalpy is going to go down. It's going to be the exothermic favorable reaction. That's a kind of cool way of demonstrating a trade-off, that when the entropy goes down, and we'll find out this is unfavorable for the process to actually happen. We have to have a favorable change in the enthalpy, and that's that downhill change of an exothermic reaction. Finally, number five, you could do this one as well. Go put on a pot of water on the stove and let it start boiling. Look at the beaker of boiling water. Now, you picture a beaker of boiling water. You've always seen this boiling water, but you probably never thought about it. Water at room temperature is not easily changed to gas. Remember, it has a low vapor pressure. But the heated water does change to gas easily. And if the water was removed from the hot plate, it would stop boiling. So you're continually adding heat to the water. So heat is going in. And so when the liquid changes to gas, heat is being absorbed. And again, you know that because if you take the water off the heat, there's no more heat to absorb and the water stops boiling. Now, this is where things get a little out of what we consider to be common sense. Even though the water is very hot, it's very hot because you've got to put energy in to get it to boil. And just like we saw when I boiled the water in the bell jar, the water had to absorb energy from somewhere. The water got colder, which meant that it's an endothermic reaction or endothermic process. And so the delta H, and this is the delta H, we call this the delta H of vaporization, is a positive 46 kilojoules for every mole of water that we have. So this is the end of the so-called demo. And from the earlier notes you took and from this demo, the post-lab questions is really the worksheet. And this is the homework. To fill in the rest of this worksheet is the homework for you for homework 13-2. All right, so get that done for the next class, and we will see you in the next class.